Hello, and welcome to another video in my series on operations management. Now this video is actually part 2 in a 2-part series on network diagrams, more specifically critical path analysis using the forward and backward pass method. So if you have no idea what I'm talking about, it's probably because you have not seen part 1. So I highly encourage you to go ahead and watch part 1 and then open up this video to watch part 2. Now I do want to remind you, if you have watched part 1 and are now in part 2, that if you go to the corresponding blog post for this problem, which is in the description under the YouTube video, you will find a link to the corresponding blog post for this problem. At the blog post you will find 2 things: a downloadable image of our network, so you can actually download the PDF, print it out, and follow right along and write in the figures as we go. You will also find a PDF file of this very PowerPoint presentation, because critical path analysis, while not hard mathematically, it is easy to get lost in all of the abbreviations. So on the blog post you will find a downloadable version of the diagram and downloadable versions of these PowerPoint slides, both in PDF form, so you can follow right along. So in part 2 we're going to actually do the critical path analysis in a drawing program. So without waiting anymore, let's go ahead and dive right in. So let's go ahead and walk through our forward pass, our backwards pass, and our critical path analysis step by step. Now to make the video go quicker, I've gone ahead and put our diagram in the middle using our new node diagrams. Now over on the left hand side, I've gone ahead and put our table with our activities and the time to complete each of those activities. And remember, the 25 at the bottom is simply how long it would take if we did each activity consecutively. So A, then B, then C, then D, etc. However, we're not going to work that way because we can do certain activities at the same time. So it should take significantly less than 25 weeks. Now above the table, I have a model of our new node diagram, and that is very similar to our old nodes, except we've put dividers in it so we can put our early start, our early finish, etc., etc. Now above that, I've gone ahead and pasted in the formulas for each piece of data we want to put in each node. So we have ES equals max EF of all immediate predecessors, etc. Now I do want to just pause here for a second. This looks a lot more complicated than it actually is. There's no advanced math involved or anything like that. It's a lot more of just thinking methodically through this project and figuring out when certain activities can start, as far as the earliest time, when's the latest start for certain activities, and so forth. It's very simple single-digit addition and subtraction, so don't freak out. We'll walk through it step by step, and at the end you'll see exactly how it works. Now in the middle, I've gone ahead and put our diagram, like I said before. Each node is already labeled with the activity, so A, B, C, D, and so forth. Now if you look over in our new node diagram on the left, we see that we have T at the bottom, and that is just the time that that activity is going to take. So I'm going to go ahead and start the first one, and then I'll pause and fill in the rest. So we know activity A is going to take 2 weeks. So we'll put a 2 there. Activity B is going to take 3 weeks. So I'll go ahead and put that there. Now I'm going to go ahead and pause the video and then fill the rest of those times in. Okay, so here is our diagram with our activity times filled in. So remember, each node is labeled with a letter. That's the activity over on the left hand side, and its time to completion, which also comes from the table on the left hand side. So we haven't really done anything new yet. This is very similar to our previous diagram. Now we're going to run through the forward pass scenario. And this is a forward walk through our diagram, taking into account any predecessor activities for each node and the completion time for each node. And once we do 1 or 2, you'll see exactly how this works. It's not complicated at all. So we're going to start over on the left hand side, of course, and the first node is our start node. So it's time 0, everything is 0 in it. That should be fairly obvious. Now let's go up to activity A, and we want to find our earliest start. So remember, activity A has no immediate predecessors. So when is our earliest start? Well, that's now. And what is that in terms of time? Time 0. So we're going to go ahead and put a 0 into the earliest start time for activity A. And this cursor is kind of hard to work with. There we go. A 0 for earliest start for activity A because it's one of the first activities we can do. There's nothing before it. And of course, activity B is the exact same. So we'll put a 0 in the earliest start time for B. And there we are. So now that we have the early start time for A and B, we can go ahead and find the earliest finish. So if we look on our table at the very top, we see the earliest finish, EF, equals our earliest start plus our activity time. So let's go to node A, activity A, and we notice that our ES is 0 and our activity time is 2. So 0 plus 2 is 2, and that is going to be our earliest finish. So we'll put a 2 in our green section, and there we go. Pretty simple. Let's go down to B. Now our ES is 0 and our activity time is now 3. So the earliest time we could complete B is after 3 weeks. So we'll go ahead and put a 3 in the green. And there we go. Pretty simple. Okay, so let's go ahead and go over to activity C, or node C. So remember, our earliest start is the maximum earliest finish of all immediate predecessors. So how many immediate predecessors does C have? Well, it only has one, and that's activity A. So the earliest finish in activity A, which is the green, is going to be our earliest start in C, which is the light blue. So that will be 2. And there we go. Now let's go down to activity D. Same principle. The earliest start will be the maximum EF of all immediate predecessors. So what are D's immediate predecessors? Well, it only has one, and that's activity B. So the blue in D will be the green in B, and that is 3. When a node only has one immediate predecessor, like C and D do, it's very simple. The ES in the second node will be the same as the EF in the first node because there's only one. Okay, so let's go ahead and figure out the earliest finish for C and D. So remember, earliest finish is our earliest start, which is the blue, plus our activity time. So for C, we just have 2 plus 2, which is 4. Okay, and now we have D, and 3 plus 4 is 7. Okay, so let's pause here and think about what we've been doing. Now remember, our earliest start is, if everything goes okay, when's the earliest time we could start on that activity? So of course for A and B it was 0, and for C it was 2, because A took 2 weeks, and for D it was 3, because B took 3 weeks. Now as far as our earliest finish go, that's just the earliest start plus the activity time in C and D. So 2 plus 2 is 4, and 3 plus 4 is 7. So at the very earliest, we're going to complete C 4 weeks in. And at the very earliest, we're going to finish D 7 weeks into the project. So it's been pretty easy from there, but now it gets a little bit more complicated. So let's go ahead and go to E, because this one will be actually fairly straightforward. Now the ES for E is the maximum EF of all immediate predecessors. How many immediate predecessors does E have? Well, it only has one, and that's activity C. So the blue ES in E will be the same as the green EF in C. So we were going to go ahead and put a 4. Into the earliest start for E. And again, that comes from the earliest finish in C. All right, let's go ahead and look at activity F. So when is the earliest start for F going to be? How many immediate predecessors does it have? Well, it only has one, and that's the same thing. It's activity C. So the earliest start in F will be the same as the earliest start in E, because they both have C as their only predecessor. And there we go. Now let's go ahead and finish out E and F, because it's fairly straightforward. Remember, the earliest finish is just the early start plus the activity time. So in E will be 4 plus 4, which is 8. And now in F, it'll be 4 plus 3, which is 7. And there we are. Now let's go ahead and look at G. Now what's going to be the earliest start, or ES, for this one? What's going to go in the blue part? Well, if you remember our definition of the earliest start, it is the maximum of all the earliest finishes in all immediate predecessors. So what are G's immediate predecessors? Well, E and D. Now in E and D, what is the highest value in the earliest finish slot, which is the green? Well, that would be in E. In E, the earliest finish is 8. So, since 8 is higher than 7, that's the maximum earliest finish. Therefore, that goes in the earliest start of G. There we go. And that should make sense, because remember, by definition in our network diagrams, that for G to begin, D and E both have to be completed. So we have to wait on E to be finished before we can begin G. Therefore, the earliest finish in E of 8 weeks is going to be the earliest start for G. Even though we may be done with D earlier, D may get done before E, but we still have to wait on E to get finished before we can start G. And in this case, that is 8 weeks. Okay, so let's go ahead and do our earliest finish for G. And remember, that's just the earliest start plus the activity time, which is 8 plus 5, and that is 13. And there we go. Now we only have, really, for the forward pass, one more node, and that's our final node of H. So let's go ahead and figure out our earliest start. And remember, our earliest start is just the maximum earliest finish of any predecessor nodes. H has 2 predecessor nodes, F and G, and we look at the earliest finish in each of those, which one's the highest, and we put that in the earliest start for H. So the green regions of F and G, one is 7, the other is 13. The maximum of those two is 13, so therefore we put 13 in the earliest start for H. And there we go. So let's go ahead and do our earliest finish for H, and that's 13 plus 2, which of course is 15. And there we go. We have gone ahead and completed the entire forward pass through the network. But what does this mean? Well, if you take a step back, each blue section of the node is our earliest start. So at the very earliest, assuming everything goes perfectly, that's the very earliest time we're going to start that activity. Now if you look at the green, that's the earliest finish. That's the earliest completion time for that activity. Now if we go all the way to the end of our diagram, how long do we expect this project to take if everything goes according to plan? Well, 15 weeks. That is going to be our earliest finish for this project. So instead of 25 weeks down in our chart, this should take 15 weeks because we can do certain activities simultaneously. All right, so I'm going to pause for a second and then we'll go ahead and do our backward pass. Okay, so let's go ahead and do our backwards pass through our network. Now to begin our backwards pass, we're going to start with the stipulation that the latest finish in our project is the same as the earliest finish. So if you look on node H on the far right, you will see that the early finish, EF in the green, and the latest finish in sort of the tan color are the same, 15 weeks. Now from there, we're going to go backward through our network. And this will all make sense when we're all done. Trust me, it's got to hang with me. Now, To figure out our purple section of our nodes, we're going to go up to our diagram. So you see LS is purple. And according to our formulas at the top left, our latest start, or LS, equals our latest finish, LF, minus our activity time. So if we go over to node H, our latest finish is 15. Our activity time is 2. Therefore, our latest start is 13. All right, and that's just 15 minus 2. Okay, so now we go backward through the diagram. So let's go up to activity F. Now we need to find the tan portion of our node, which is the LF, okay, our latest finish. And we do that by looking for the minimum latest start of all immediately following activities. So ahead of it in our network. So the only node ahead of F in our diagram is H. So what is the LS, or the latest start, in H? Well, we just did it. It's 13. So the purple section of H is 13. So that is the tan section in F. And there we go. Now we'll go ahead and figure out our latest start, which is the purple. And remember, that is just the LF minus our activity time. So we have 13 minus 3, and that is 10. There we go. Let's go down to G. Let's go ahead and find our latest finish. So remember that that is just the minimum late start of all activities following it. So just like F, the only activity following G is H, and of course the latest start in H is 13. There we go. And again, that just came from the purple section in H, the latest start. So let's go ahead and figure out our latest start for G, and that's just 13 minus 5, which is 8. Okay, there we go. Now again, you are watching a video online, so if you need to pause it to stop and think about each step, go ahead and do so and just start it up again. So I know the math is not hard, but you have to think about how you're going through the network, and that can get kind of confusing with all the ESs and ATs and LFs and stuff like that. Okay, let's go ahead and proceed. Now, why can't we go to C from here? Well, remember that our backwards pass requires all of the immediately following nodes to be completed. But if we go to C now from F, we can't do that because E isn't finished yet. So you have to be very careful as you proceed backwards through the diagram. So we'll do C here in a minute. Now we can either choose to do E or D. And luckily they're both pretty much the same. So remember, in E, we need to look for the minimum LS in any immediately following activities. There's only one, that's G. G is the only immediate following activity from E. So the purple section in G, which is the LS, is 8. So that will be our LF in E. So there we go. And the same thing for D. D only has one immediate follower, and that is G. So the purple in G, which is the LS, will be the LF in D. So 8. And there we go. Now we can go ahead and go to C. So if we look up at our formulas, the LF, which is the tan color, is the minimum LS of all immediately following activities. So F immediately follows C, and E immediately follows C. So what are the LS values in those two? Well, we don't know that yet because we haven't figured out the LS's for E and D. So let's go ahead and do that. For D, remember, it's just 8 minus 4, so that is 4. And in E, 8 minus 4 as well, so that's 4. All right, now we can proceed to C. So we need the minimum LS of everything that immediately follows C. So we have a LS of 4 in E and an LS of 10 in F. So the question is, which one of those two is the minimum value? Well, of course, it's the 4. So our 4 will be our LF in C. There we go. Let's go ahead and do our subtraction to find our late start, or LS in C, and that's just 4 minus 2, which is 2. Good. Now we're almost home free because we're almost back to our start. So let's go ahead and find our latest finish, or LF, for A. So it's going to be the minimum LS of anything immediately following A. There's only one thing, and that is C. So the LS in C is 2. Therefore, the LF in A will be 2. There we go. And then we'll go ahead and do our subtraction to find our LS in A, and 2 minus 2 is 0. Okay, let's go down to B. And remember that in B, the LF will just be the LS in D. That's funny. Will just be the LS in D, which is 4. I didn't plan that, really. Just kind of turned out that way. And there we are. And then again, to find the LS in B, it's just 4 minus 3, which is 1. And there you are. Congratulations, you have just completed your probably first, forward and backward pass through a project management diagram. So we need to talk about one more thing before we finish with the diagram. Now if we go through our diagram, let's say we go to activity A, notice that our latest and earliest starts are both 0. We're going to start at 0 weeks, or now, regardless. But now look at B. Our earliest start is 0. That means we can start immediately. But in this case, we have a latest start of 1 week. Well, what does that mean? And this is a product of our forward and backward pass. It tells us a lot of information that we could not get from a simple diagram. We could conceivably wait 1 week to begin activity B. That's our latest start. Now, if we go forward from A to C, notice our starts are the same. But if we go from B to D, again, our earliest start and latest start are 1 week apart. Now if we go from C to F, now look at that. We have an earliest possible start of 4 weeks and a latest possible start of 10 weeks. So we could conceivably start activity F anywhere from week 4 to week 10. Now if we go down to E, the starts are the same. Go down to G, the starts are the same. And if we go over to H, of course, the start and finish are the same there. Now this introduces an important idea in our network diagram called slack. And just like a rope or a piece of string has slack in it that you can pull it tighter, that's the exact same way you can think of slack in a project management diagram. So anytime our latest start is greater than our earliest start, we call that slack. And we go ahead and write that into our diagram. So in this case, I've chosen red. So down at B, we have 1 minus 0, so we have a slack of 1 week. So our slack is 1 there. Now for A, we don't have any slack at all. C, we have no slack. D, we have 1 week of slack. So we'll type that in there. Now E, there's no slack. In G, there's no slack. Let's go up to F. Well, of course, we have 10 minus 4. That's 6 weeks of slack in F. Then we go on to H, no slack there. So what does this actually mean? Well, if we delayed B by 1 week, that would also affect D, because you got to think of B and D on the same string in the diagram. So if we wait on B, we're going to use up the slack that's common to them, which is that 1 week, because the slack week in B is the reason D has a slack week. So if we wait on B, D will also lose its slack week. Now up in F, that's not tied to any other slack node for any other, or anything else. So F is a very flexible activity. We could start that anytime between 4 and 10 weeks and it won't affect anything else in our project, whereas B and D are tied together, figuratively and literally. So you got to think about those two things with Slack, that they do affect the nodes next to them. And finally, we're at the idea of critical path. What is the critical path through our network? Well, the critical path is the path that leads through our network that has no slack. So which path has no slack? Well, we start and then we go to A, to C, to E, to G, and to H. And sort of the common way of saying there's no slack is that there is absolutely no wiggle room going through those activities. So the starts and finishes have to be spot on. There is no waiting around for any activity in that path. So we define the critical path as starting at our beginning activity, ending at our ending activity, and proceeding through the network without crossing any node that has slack. But what does that mean in the real world of project management? Well, there is absolutely no wiggle room for our critical path. So if at the beginning of the project we send a team to A and a team to B, and let's say the team at A is running a little bit behind, we can pull workers off project B and have them work on A because B has some slack time in it. We can actually move resources around to make sure A stays on the critical path. Now, if we do that and B runs over into the next week, that's also going to affect D. So we do have to keep that in mind. Now, as we proceed to the diagram, as we send workers to F, they could conceivably be there for 6 weeks. There is no hurry at all in activity F. So we could pull workers off F basically at whim, as long as it gets done, by its earliest start time, or latest start time, which is 10 weeks. So it just tells us how we can allocate resources, the absolute critical path we must stay on so our project ends on time, and where we have some wiggle room as far as pulling resources off certain activities and onto others to make sure the critical path is met. And we could not do that without doing our forward and backward pass, and therein lies its value. Okay, so that wraps up our 2-part series on critical path analysis using the forward and backward pass method. Now, in our network diagram, that helps us answer a few questions. Number 1, if everything goes according to plan, when we can expect our project to be completed? Since some of our activities can occur at the same time, it will take a lot less time than if we did each activity consecutively. So this method helps us calculate that. Also, which activities in our project are along the critical path? Meaning that in order for the project to be completed when we project, those activities must stay on time target. 3. Which activities in our project have some slack time? Meaning that if an activity along the critical path is running behind, we could move resources, whether it be labor or equipment, over to an activity on the critical path in order to make sure it's completed on time, and then move it back to an activity that has slack time. Without doing this method, we could not know that. So all in all, the forward and backward pass method helps us, 1, finish our project on time, allocate our resources effectively, and make sure that every activity along our critical path finishes when it's supposed to. So again, thank you for watching, and I look forward to seeing you next time.